Okay. So good afternoon, everyone. So I'm Yufeng from UT Austin. So this is a joint work with Oscar Bastoni, Ruben Martins, and Ishu Dilix, and Saswar Nat. So everyone is using cell phone right now, right? So you might already aware that an Android malware can steal your personal information, such as like a bank account, credit card number, etc. You might also heard of that. You can even hack into your a medical system that causes a bunch of financial loss. But you might not be able to aware the fact that by the end of last year, you just managed to steal a Tesla car. Okay. So despite the fact that many research are trying to improve the overall detection rate for malware, so its number are still growing dramatically. Like here is the number in the last 6 months. Like about 37 million of malware instances are being detected. And since the majority of antivirus companies manage those malware instances by classifying them into different families based on their common behavior. So if you look into this number in a bit more closer, you will find that they actually come from less than 300 malware families. So this gives us an opportunity that if we can manage to describe the semantic behavior for those hundreds of like malware families, we might potentially capture millions of malware instances in the market. So how are we going to do that? So since we are going to build on top of our previous system, Apposcopy, so I would like to do a quick detour in one slide. So as you can see, the workflow, So on the left-hand side, we provide high-level language for the end user to describe the semantic behavior of a given Android malware family. And then you dump that into a signature database. And then on the other hand, so given an Android application, we design a novel static analysis to figure out whether the given application belongs to existing malware families or not. So if you just look at the overview of this picture, you can figure out that there is at least 2 caveats. So the first one is really tedious and error-prone for a human to write down those semantic like signature. And second, since we are using signature, even we are based on semantic properties, so we are still vulnerable to like semantic obfuscation. So to mitigate this kind of problem, so our goal in this new system called Asteroid is first we would like to get rid of the manual effort by automatically synthesize like semantic malware signature from very few samples. Okay, and then after we have this signature as what we did before, given an Android application, we also like to come up with an approximate matching algorithm. First, to decide whether a given app belongs to our current like signature in the database. And second, it should also be resistant to semantic obfuscation. So how are we going to do that? So before I introduce the problem of signature inference, I would like to clarify what I mean by signature. So a signature is a graph, so used in our previous work. Basically, given an Android application, you convert into a graph representation called intercomponent code graph. As you can see that each node in our current code graph is a component in Android, okay? So as you can see, there is activity, there is service, broadcast receiver, etc. For those of you don't familiar with Android application, you can just think of it's a base building block for building an Android application. And then all the components are communicated through what we call intent objects, okay? So this is the node is a component. And then for the edge between the component, we have that solid line to denote like the control flow dependency. Like here, as you can see that there is an edge between activity 1 to service 1. It means that the activity 1 can launch service 1, okay? In addition to a solid line, we also have dashed line to correspond to the data flow property. Like here, an example is information flow. Like here, between activity activity 1 and activity 2, so there is an information flow that leak your device ID through the internet. So for every given Android application, we convert into this high-level graph representation. And on the other hand, so if you look at the signature, the one on the right-hand side, we also provide a high-level language for the user to describe the behavior of a given family. As you can see, there are 3 key ingredients. So you have a component predicate to specify the type of your component. Like here, R is a receiver. And you can also like use a control predicate to denote that this component R can launch another component S of type service. okay? And finally, you can also use flow predicate like to denote that inside this component S, you can produce an information flow that leak your device ID through the internet. So once you have this kind of high-level graph representation, you can map the description back to the original description of the Android application and to check whether it matches your behavior or not. So once we have the signature, we can define our problem of signature inference like the following. So given n sample from a family F, we would like to compute its signature S, okay? So an ideal approach is you just need to find like any signature that's match current n sample. So, but that wouldn't work because like even an empty signature will match this criteria. So in order to generate some signature that are actually meaningful, we really want to refine our previous requirement to find, if you want to find a candidate signature S, first you need to make sure that it needs to be a common subgraph of your of given n instance. Otherwise, you will generate false negative immediately, okay? And then in addition to this requirement, you also want the signature to be maximally suspicious. So the intuition is that, so you want that, your representation to capture the key malicious behavior that only shared by the current family of the given instance. The intuition is to minimize the number of false positives, okay? And then we can reduce the problem of infer a signature to computing a maximum common subgraph, okay? So let's take a look at a concrete example. Suppose we are given like two samples from the same family. Okay, they are doing completely two different stuffs. And then assume that we already analyze and generate our graph representation based on our previous work. As you can see here, I use different shape, rectangle, ellipses, and diamond to denote different type of the component. And we also have control property and data flow property. Now as a human, so in order to figure out what's the signature here, so the first requirement is, first you need to satisfy it's a common subgraph, okay? In this case, it's not very easy, not very hard to figure out some candidate because I already labeled them in different colors, okay? Now you want to figure out which one is the correct candidate. So if you recall our previous second criterion, you need your behavior to be maximally suspicious. Then it's not very hard to figure out it's the first one because it's doing a lot of suspicious stuff, like it's listening some suspicious event, launch a background service, and produce a bunch of things flow. And it's okay to do this manually, but what happens if you have more than two samples and the graph size is bigger? So we really want some approach to automate this process. So if you recall our previous workflow, we first reduce the problem of signature inference to computing the maximally suspicious common subgraph. Since this problem is very hard in general, so we further reduce the problem to standard MaxSat, where we can find an off-the-shelf solver to give us a solution. So to say what I mean by MaxSat, so given an unset formula in Boolean conjunctive normal form, which is initially unset, okay? And then we would like to determine the maximum number of satisfied clauses. Note that in MaxSat, we have hard clause to denote the clause you have to satisfy. And we have soft clause to denote that we prefer them to satisfy, but it's okay if some of them doesn't. And since some of the clauses are more important than the other, you would like to assign them with different weight. And at the end, you would like to find an assignment such that so the total weight of your satisfied clauses is maximized, okay? And then going back to the context of signature inference, so we would like to use a hard clause to model the requirement of common subgraph. And then similar, we would like to use soft clause to approximate the requirement of maximally suspicious, which correspond to the data flow property. And then since some properties are more important than the other, we would like to assign them with different weight. So at the end, we will get an objective function like the one on the bottom. So you don't need to figure out like what it means. Just keep in mind there was some hard constraint and soft constraint, which correspond to control property and data flow property respectively. Now let's go back to our previous example and see how it works. Let's assume that all the properties are of the same importance, like they are all just weight 1. In this case, to compute the object function, you just need to count the number of occurrences of semantic property. For the first candidate, you got 6, and then you got 4 and 3 for the second and third one. Since the first one is the maximum, you pick it as a signature. Okay. Now that you have the signature, So the second thing you need to figure out is what if I want to detect an application? In this case, we would like to utilize our previous inference algorithm that I described before by saying that in order to decide if a sample A belongs to a family F, let's take the signature of this family F as a special sample. Meaning that, so given those two samples, you trigger the previous inference algorithm to say, give me a new signature S prime. And then in this case, you compute the similarity between this S prime and S of F. So if their similarity is higher than a certain threshold, you still believe that it belongs to that family. Okay. Now let's resume our example. Suppose we want to use the signature from the left-hand side to detect the sample on the right-hand side. In this case, the hacker is very smart, and then he removed one of the property. If you are still looking for like exact matching, it's going to fail. So what we did here, we take the signature on the left-hand side as a special sample, and we triggered the inference algorithm, which gave us a new signature like the one on the bottom. So if you look at the new signature, which I show on the right-hand side, they are almost identical to the first one, except one difference in terms of data property. So since they are so similar, we still conclude that they belong to that family. And note that this simple extension gives us the ability to resist to semantic obfuscation. So to evaluate our tool, we try to answer like 3 different questions. Like first, what's the quality of the signature synthesized by our tool? So compared to the manual version, are they better or worse? Okay. And then the second, so we would like to answer how effective is our approximate matching in terms of like detecting the zero-day malware. So finally, we would like to also compare the performance of our tool in terms of false positive and false negative with state of the art. Okay. So for the first experiment, we run our current system on the benchmark, Android genomic benchmark, which are being used in our previous work and also by other related literature. So in our previous work for those family on the X value, we spent more than a month to manually write down their signature. And then finally, we get a detection rate of about like 90%. Okay. And then for our current systems, so for each family, so we pick some of the sample and automatically synthesize the signature and run the signature on the rest of the remaining benchmark. As you can see, we achieve a detection rate of 94%, which shows that our automatic version actually outperformed the manual version. So second, in order to evaluate our tool on 0 day, so first we pick 160 malware from McAfee and Semantic, of which we don't have signature on our current database, and completely destroyed. So we compare our tool against the state-of-the-art MaxSat, and the numbers show their corresponding detection rate. As you can see in this data set, we can detect more malware instances compared to the state-of-the-art. So another interesting observation is when we apply our tool back to the benign application from Google Play, like we actually identify 22 applications from Google Play that cannot be detected by any of existing antivirus tools, but they are actually malicious after fully manual inspection. So this experiment showed that our approximate matching algorithm is actually effective to help us detecting 0 day. So finally, we also compare our tool against 2 state-of-the-art, namely Driving and MaxSat. So the first part of the numbers is correspond to the false positive. So false positive on the benign application. For the false positive on Driving is relatively easier to evaluate because we share the same set of benign application. But for the part on MaxSat, it's a bit tricky because we have to trigger their web service, and then we cannot do like large data set evaluation. At the end, we randomly pick around 500 samples from this benign data set, and then MaxSat marked like 175 of them as malicious. So at the end, and then after, this is the false positive. So we also evaluated on the malware benchmark that we used in our first experiment. So as you can see that while Driving can detect like 89% of the malware instance, and MaxSat can detect 84% of them, whereas our tool, Asteroid, can detect 94% of the malware instance. So this experiment showed that our tool can achieve a higher detection rate with low false positive compared to state-of-the-art. So to conclude my talk. So basically, we present a new system called Asteroid, which help us to automatically infer semantic malware signature from very few samples. And then we also do experiment to show that our approximate matching algorithm help us to resist to common like semantic obfuscation. And that concludes my talks, and thank you for listening, and I'm happy to answering questions. Thank you.
Hey, Manuel.